Hello everyone, my name is Siddharth Ashokan. I'll be presenting on the Euler-Lagrange analysis of generative adversarial networks, which is a JMLR paper and part of the NeurIPS 2023 Journal to Conference track. This work was carried out as part of my PhD at the Robert Bosch Center for Cyberphysical Systems at the Indian Institute of Science, Bangalore, India. And my co-author on this paper is Professor Chandrasekhar Seelamantula, also from the Indian Institute of Science. Before we begin with the specifics of the paper, let's start with a brief introduction to GANs, a generative modeling framework for transforming noise to images. GANs model a min-max game where the target to be modeled, which in this case are Medface's images, can be viewed as coming from an underlying distribution P suffix d. The generator then learns to transform parametric noise, typically Gaussian distributed, into samples following an output distribution P suffix g. The discriminator network is tasked with differentiating between the real and generated samples and relay this information back to the generator through appropriately defined loss functions. Let's focus a bit on the losses used to train various GANs. Broadly speaking, there are two kinds. The first and the classical formulation is that of divergence minimization. For example, the standard GAN involves a cross-entropy loss, and the generator can be viewed as minimizing the Jensen-Shannon divergence between the data distribution PD and the generator distribution PG. Similarly, the ELeGAnt considers a least squares loss corresponding to the Pearson chi-square divergence. On the other hand, we have integral probability metric GANs such as the Wasserstein, Sobolev, and Fisher GANs, where the choice of IPM results in a corresponding constraint class for the discriminator, the most popular among which is WGAN, which consider Lipschitz-1 discriminators. In practice, however, the Lipschitz constraint is challenging to implement, and variants such as WGAN GP, WGAN LP, etc. enforce a gradient penalty to approximate the constraint. A key ingredient in our analysis is variational calculus, from which we consider the optimization of integral loss functions leveraging the conditions of the first variation, known popularly as the Euler-Lagrange condition, to derive optimal discriminators in GANs. In this paper, we analyze various FGAN and WGAN variants within the functional calculus framework. In particular, for WGANs with a novel variant of the gradient norm penalty, we showed that the optimal discriminator solves a Poisson PDE and subsequently derived the solution via a Fourier series approximation. We demonstrate superior performance on latent space learning tasks considering Wasserstein autoencoders. While we summarize a few key results here, in-depth analysis can be found within the journal manuscript. As an example, consider the standard GAN loss. The expectations, rewritten in their integral form, fit within the Euler-Lagrange analysis framework, the integrals being defined over the convex hull of the supports of PD and PG. Applying the EL condition yields the optimal SGAN discriminator, which is consistent with the result derived with pointwise optimization in the baseline work. The EL approach also yields the desired optimality condition that PG star is PD, the data distribution, when considering regularizers that enforce PG to be a valid distribution. For similar derivations for all major FGAN variants, be sure to check out the paper. We also derive general solutions to non-saturating GAN losses and LSGAN with various choices of class labels. A more interesting use case is the WGAN loss with a gradient norm penalty enforced uniformly over the support script X, which when analyzed within the EL framework yields a Poisson partial differential equation that governs the optimal discriminator D star. In this work, we explore a Fourier series approach to solving this PDE. Considering the Fourier series expansions of PD, PG, and D star, we showed that the Fourier coefficients of PD and PG can be computed by evaluating a sample estimate of the characteristic function at the desired harmonic omega m. This gives us a closed-form solution to the coefficients of the discriminator. While detailed truncation and approximation error analysis are presented in the paper, the resulting Fourier-based discriminator is implementable via a two-layer network with pre-computed weights and sinusoidal activations. As a use case, we employed the closed-form discriminator in latent space matching tasks using Wasserstein autoencoders, giving rise to the wafer framework. Wafer demonstrated superior performance with improved convergence without the need for training a classical GAN discriminator. These are also corroborated in terms of FID, reconstruction error, and image sharpness metrics on various standard image datasets. In conclusion, we analyzed various FGAN and WGAN variants within the EL framework and showed that the optimal WGAN discriminator solves a Poisson PDE implementable by means of a Fourier series approximation. As part of the future scope, we will analyze cycle-consistent, relativistic, and other GAN variants within the proposed framework and also explore alternative solutions to the Poisson PDE. These are the key references cited. And with that, I'd like to thank you all for your attention and conclude my talk.